Good afternoon, everyone. I'm back. I'm here to deliver another lesson from the second half of AP Calculus BC. In this video, I'm going to focus on a new power series or new Maclaurin polynomial rule, one that's going to be pretty powerful and be pretty helpful for us, as well as to demonstrate some arithmetic operations you can do with different power series and polynomials to save you a little bit of trouble so that you don't have to do that massive differentiation work that you had to do at the very beginning. So today's not going to really be a new concept. I don't think you're really going to see anything new today. I think there's even probably an argument that other than some like algebraic structural tricks or techniques I'm going to demonstrate for you, truth is you could probably do a lot of this stuff, so it should move fairly quickly compared to other things. I'm going to basically make my goal to demonstrate each thing once, give you a try it, an opportunity to work with some stuff, and then do the same thing with the other half. And there are only really two parts in here as well. I will throw in something that just kind of like blows my mind at the very end, but that's as I'm wont to do. So having said that, before I begin, just as that kind of daily check-in here, as I'm trying to do, I know many of you actually do watch these videos from the beginning, so if you're looking for small things to check in, I believe this last night was the largest single increase in fatalities related to the virus, so that's kind of a sad, sobering fact. Other than that, we're seeing some of the same kinds of stuff, like teachers in Elk Grove are gearing up for distance learning kicking off. So obviously I've been preparing ahead of time for that. So you'll be watching this and using that as a tool to support you in your distance learning of Calculus BC. Still waiting on some word and information about other things like grading, but I'm sure that will come. Other than that, on like more personal stuff, been working on a big video project. I'm nearing the latter portion of that, so I'm hoping that I'll be able to unveil that at some point and wrap it all up. Definitely have had some fun with it, but also been challenged by it. Other than that, like started reading a book again, so trying to make that my third book of the hiatus. Hadn't been reading a whole lot before that point, so there's always something good. I guess that's something good to come out of it. And then I got convinced by a number of people, including some of you, to actually try playing the game. I think it's called Animal Crossing New Horizons. So I checked that out. Took a look at that this morning. Played my first half hour of Animal Crossing. Did a lot of weeding there, even though I definitely don't want to weed in the real world and be terrible for my back. So I guess it's a nice little distraction to go with the other things and the schedule I've kind of built up. So I hope you're all doing well. Hope this video finds you well and gives you some distraction, as always, from the stuff. I know if I don't have something to do, I tend to turn on the news and just kind of listen to the news, and it doesn't usually make me feel real great, even when experts are talking, even when we're talking about how much we've already started to flatten the curve. Just kind of a scary thought. So having said that, Animal Crossing. So that's always something good. So with that said, let's go ahead and kick off the lesson itself. In fact, let me just kind of get my pen here. There it is. So, having said that, in this lesson, which is titled Geometric Power Series and More, like we're going to do about equal, we're going to do some geometric power series work, and then we'll do some more other stuff, like we'll talk about some other operations that are up there. Where I wanted to begin was just kind of remind you of those things that we kind of have to take as a given at this point. And this is going to be that first lesson where it's going to be really, really valuable and crucial that you already know these power series. So these are, as you can see, the power series or Taylor polynomials, Maclaurin polynomials. I guess these are Maclaurin because they're centered at 0 for cosine, sine, and e. Now, or in e to the x. So of course, what's something that makes these three functions very special is the fact that they have, based on yesterday's work, an infinite radius of convergence, meaning that they converge for all values, which we've seen visually as represented by the fact that the more terms you add to your polynomial or series, the more accurate you get. Like you get further and further out accuracy from the center at 0. So I just want to put those up there, just as kind of a reminder that these are the things that you do kind of need to know. It's not that you couldn't derive them yourself and do the differentiation to get there, but it's helpful just to know these right off the top of your head so you don't have to do that. These are taken as a given that you can find really quickly. A good reason to bring these up at the beginning of the lesson is, of course, we want to add to this. Like we are going to add today one more series, which will be just as crucial and important for you to know. It won't have that infinite interval of convergence, and in fact, you'll see why as soon as we get into it. But for now, I just want to point out that this is our list up to this point. We're going to add one more on there. Anything else we come up with, I would either have to give you or you would have to compute by hand as you work through things. So having said that, here's what we know. Let's actually begin today with kind of a throwback problem to move us towards that fourth, we'll call it special Maclaurin series or special Maclaurin polynomial. So right here, I put this as a little r up here. If you are wondering why that's there, is that a joke? I'll count it as one. If you're wondering why that's there, it stands for review. In a sense, we're going to use this as a method of reviewing the techniques we've used up to this point to generate a Maclaurin polynomial. And in this case, it does ask us for a Maclaurin, which means it's centered at 0, which will be helpful. Truthfully, we've had shortcuts for a lot of these things lately, but this is not actually one of those situations where it's going to be, where that's going to be an option for us. So let's actually just jump in and do it the old-fashioned way, as I said. So what do I mean by the old-fashioned way? I mean we're going to generate some terms here until we develop a pattern. So we're going to differentiate a couple times. So if you'll recall, the first thing that we did when we started with Maclaurin and Taylor polynomials was we started by figuring out values of the function. So obviously f of x is equal to 1 over 1 minus x. Now having said that, let me point out though that there is another way we could write this function. It's going to be slightly easier for us to differentiate. The reason I'm holding back right now is, of course, the derivative of the denominator is negative 1, which means that we would have to deal with the chain rule in some way, or possibly the quotient rule even. So what I want to do is I just want to, with your permission, rewrite this function as negative 1 over the quantity x minus 1. That way our denominator's derivative is just 1, and we can work with this a little more cleanly. So to kick things off, I'm going to begin there. I'm going to rewrite f of x as this. Of course, we will plug into it in just a second, but for the moment, I'd rather calculate a few derivatives. So from here, if we take the derivative of this thing, keep in mind that that is the same thing as negative quantity x minus 1 to the negative 1 power, right? Same thing. So basically from there, if that's true, our derivative is going to be positive 1 over x minus 1 squared. So there is our first derivative. After that, we can kind of follow the pattern pretty effectively. The second derivative is going to be negative 2 over x minus 1 cubed. Our third derivative, it's always nice to get a third one in there. Our third derivative, since our power is now negative 3, that's going to give us positive 6 over x minus 1 to the fourth. And then we'll go to a fourth derivative here, why not? That's going to be, it looks like negative 24 over x minus 1 to the fifth. And there we go. We've got a few derivatives in there. Obviously, it started as just kind of an algebraic trick to kind of get us in position to differentiate. But now that we got them, we're in pretty good shape. So I'm going to space these out just a little bit, just so I can play a little bit more readily. Boom. There we go. Okay. So here's where we're at. Actually, you know what? Let's move this up just a little bit. Let's just give us a little more room to write. Okay, give me. I want more room to write. I want the space. When you live in a very tight box all the time, all by yourself, you start to feel a little constricted, I guess, a little more claustrophobic than normal. Okay, so now that we've found the function and its derivatives up to a certain point, and again, our goal is to write a formula for the very end, but for now we're okay. The next thing we want to do is we want to take advantage of the fact that we're talking about a Maclaurin polynomial, which means we want to plug in x equals 0 to each of these. So I'm going to evaluate this at x equals 0 each time. And again, the reason for this is we're trying to figure out what those coefficients will be so that this polynomial or series we construct matches the original function, 1 over 1 minus x, at every derivative. Now when we do this, again, my recommendation is you draw arrows instead of equal signs. We talked about y in the first lecture of this unit. When we plug in 0, we get negative 1 over negative 1, which is positive 1. And then, of course, we'll have to divide by 0 factorial, which is equal to 1. On the next one, if we plug in 0, we're going to get 1 over negative 1 squared, which is just 1. That's kind of cool. And divided by 1 factorial is equal to 1. Cool. Let's do the next one. This one will be negative 2 over negative 1 to the third. That's going to become positive 2. From there, we'll divide by 2 factorial, which is equal to 1. Cool, that's always nice. I feel like we've already won. So on the next one, if we plug in 0, we'll get 6 over negative 1 to the fourth. Well, negative 1 to the fourth is going to become positive 1. So this will be 6 divided by 3 factorial. And I'm pretty sure 3 factorial is 6. So 6 divided by 6 is, well, 1. And then finally, we'll go one more here. We'll have negative 24 over negative 1 to the 5th. Well, negative 1 to an odd power would be negative as well. So this will be equal to 24. When we divide by 4 factorial, we get 24 over 4 times 6, which is 1. So that's not really a surprise to me. I'm acting at this point, yes. I'm demonstrating my Thespian range. Yeah, it turns out to be 1 every single time. This is a special function. And in fact, if you haven't seen it already, you'll recognize in just a second why it is that this is special. But what's kind of interesting is you can probably at this point predict what's going to happen with the rest of them. They're all just going to give you coefficients of 1. Doesn't matter which one you happen to look at. Like, all of these things eventually will indeed give us 1. At 0 at least. Again, at 0 because we're doing a Maclaurin. What that means for us is that if we combine all this information together, we can state that 1 over 1 minus x is going to be equal to 1 plus 1x plus 1x squared plus 1x cubed plus 1x to the 4th. And at this point, I would hope that although we have not seen this particular Maclaurin series before, that you would recognize that this is actually a familiar foe. Or friend, depending on what you're thinking on. The truth is, this is pretty easy to generate a general term for. It looks like every single time we're adding just x to the n power. First one's x to the 0, then x to the 1, 2, 3, 4. They're all positive. They're all working really, really well. And from there, that means that we seem to have found our expression. It looks to me like this is just the power series, starting at 0 and going up to infinity, of x to the n. Oops, and I forgot an equal sign. My bad. Okay, actually, let me fix that because that just looked wrong to me. Oh, come on, what is my computer doing? Okay, so there we go. So what have we found? We've found the power series. But yeah, maybe this hasn't jumped out at you yet, but take a look at this for a second. What do we recognize about this series? Like, what are we doing? It looks like we're multiplying by x over and over again. That means that this series is geometric. So we actually have just found a power series that happens to be a geometric series. And importantly enough, in the geometric series, we know that the only way that this series is going to converge is going to be, and actually we'll just write this as converges. Sorry, I'm like modifying this as I go because I think I can make it a little more organized with this space. This converges, this geometric series converges, if the absolute value of the ratio, which in this case is x, since we're multiplying it a bunch of times, is less than 1. That means that in a sense, what we've just shown is that this series, this geometric power series, has interval of convergence that we don't need to actually calculate it. We know, because of the fact that this is geometric, that the interval of convergence is going to be for x values between -1 and 1. So just kind of a neat thing. So while this isn't quite as nice as the sine and cosine ones that have that factorial that remains in the denominator, which allows us to then be able to say that it converges everywhere, in this case we have a built-in one where the interval of convergence is known. And the truth is, when I said we were going to add a fourth one to our list, this is now that fourth one that we want to add. And I didn't quite space it quite as well, but there it is. Actually, I'll put a different color there just to celebrate it. There is our fourth special series. So we're going to be using this series extensively. Okay, we're going to use this series a little bit. It'll be extensive today. After that point, it just becomes kind of one of the gang, and it just kind of sticks around and is a member of the club. A prominent member. Like it's an officer, but you know, it's just one of the great officers this club of special series has. So having said that, that's where we begin. Just kind of this cool discovery that there's actually this other rational function, and that is 1 over 1 minus x is just a pretty benign looking rational function, but a rational function that has a very special power series that we already know a lot of stuff about. So we have some insight. By the way, the last thing I'll point out before we go talk about this and use this information to our advantage in the first example, I just want to point out here really quickly. This actually, excuse me. This actually should look kind of familiar. I'm not sure if anyone realizes this, but this is really the same thing as a sub 1 over 1 minus r, which we know is the sum of the infinite geometric series 1 plus r squared plus dot 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 on to infinity. So actually this is a familiar structure in itself. We just weren't looking for it at the time, because why would we have been? We were thinking in a Taylor-Maclaurin power series kind of mode. Turns out that it has some neat facts about it as well. Okay, so what is it that we're going to do with this power series? The truth is, one of the few unique things that's kind of even different about today's lesson is we want to be able to work with this geometric power series so that we can avoid having to do crunchy differentiation that makes it prohibitively difficult to determine a particular power series for a rational expression. So in a sense, this is kind of the manipulating the geometric power series portion of the unit. So before we begin, I'm just going to put this up here. This is kind of our model. This is our inspiration. We're going to try to work through and leverage this structure that we have here, that 1 over 1 minus x is this particular geometric power series. And I should point out that this is only true for, and I'll write this in there just so it's covered, for -1 less than x less than 1. So let's make sure that's covered as well. Okay, so what do we want to do? We want to construct the power series, just like this one has, but specifically for another rational expression. In this case, we want to construct it for, and I'm going to go ahead and just put this on there, for 5x, let's make this a little more interesting, for the function 5x over x squared plus 4. So we want to come up with a power series the same way. As the instructions say, we want 4 non-zero terms and the general term of the Maclaurin polynomial for this guy. You could also call it the power series for this guy, your call. So to get here, let me point this out first. This is not a reasonable strategy for us, especially with me putting that x in there. And the reason for that is, it's not reasonable because differentiating this is just super involved. It's kind of intense. It's not hard. I know you could do it. Don't let me say, I'm not telling you you can't do it. I'm not challenging you. I'm just telling you it would be crunchy. It's annoying. It's not a fun task to do, to differentiate a rational expression a bunch of times and then hopefully see the pattern. So instead, what I want to do is I want to try to find some way for us to transform this into the form that's going to look like stuff times 1 over 1 minus x. So I'll put it this way. It'll be stuff times 1 over 1 minus x. That's what we're shooting for. We want to transform this thing structurally. And for some reason, I'm just not happy with the stuff. There. We want to do this. So we want it to look like this. So what I'm going to demonstrate for you is the algebraic technique that I'm going to follow to get there. Basically, I'm going to attempt to pull things out until I see the structure 1 over 1 minus stuff. So here's what I mean. Let's take a look. I'll use this. I'll use my purple color. So the first thing I'm going to point out is I'm just going to try to get these 1s here. I'm going to attempt to get 1s in those two positions. So I'll start with the numerator. If I factor out a 5x, what that will leave me with in my rational expression is 1 over x squared plus 4. So that first move immediately, like, click, we're good. We've got the numerator correct. Yeah, there's a 5x there, but we know we can distribute in monomials like 5x into our polynomial, so I like what I see already. Our problem, though, is the denominator is still kind of a mess. So we want to get a structure that looks like 1 minus x, or if not, 1 minus stuff at the very least. So in this case, I'm going to do a couple different moves here. Obviously, I'll keep that 5x hanging out in front. My numerator is going to stick around as 1, although I don't like that fraction bar. No. There it is. Down below, I want to rewrite this first as 4 minus a negative x squared. So if you're wondering what my thought process was there, obviously there's a 4 right there, so we're not done with everything just yet. But the important thing was to get it to match the structure of minus something. So now that we have 4 minus a negative x squared, we now have the minus sign fitting in place. So it looks like we're in good position. The only thing that's left, though, is we still got to get a 1 there. And right now we have a 4. So how do we attack that? Pretty simply. What I'm going to do is I'm going to factor out a 4 from the denominator. So when that happens, that's going to, of course, bring out a 4 in front. We'll make sure. We'll distribute this out at the end just to make sure we did it correctly. But I'm going to pull out a 4 from the denominator. When I do, that leaves me with a 1 in that first spot. That's what we wanted. Remember, we wanted it to look like 1 over 1 minus something. And then we'll have 1 minus. But because we pulled out a 4 and there was no 4 in that latter portion, what we need to make sure we have in here is negative x squared divided by 4. And so therefore now what we have is we now have something that's in the position where the x used to be. So we now have something a little bit interesting being substituted into, there it is, substituted into our power series. So we're going to have to deal with that. We also have a bunch of stuff on the outside. We can deal with that as well. But now this looks a whole lot more like this. It has the 1 over 1 minus, and then there's just something in there for us to work with. So important place to begin, but I think we've just accomplished it. If you don't trust this, you're welcome to distribute this in. If you distribute this in, you'll end up with, it looks like 5x in the numerator over 4 minus 4 times negative x squared over 4. That, of course, becomes 5x over 4, and it becomes minus a negative x squared. And you'll see that that does indeed match our original function. So in other words, we've done this correctly. So we have an accurate representation of our series, or of our function. We've just rewritten it in a way that it matches the 1 over 1 minus x structure from before. Now, having said that, this might not seem like we've accomplished a whole lot. I mean, it's pretty crunchy as it is. Like, this is a full box of Rice Krispie treats here. They're Wait, is that crunchy? I don't know. I thought I had a metaphor there. I will withhold the laugh button because it didn't work. But there was a glorious metaphor in there about breakfast cereal, I'm sure. So what do? What does this all accomplish? Well, what we want to go back to is the structure that we know. We know that 1 over 1 minus x is equal to 1 plus x squared plus x cubed. And notice we want 4 non-zero terms, so that looks like a good enough one. And then plus dot dot dot, that general term x to the n. So we know that this is the Maclaurin series or Maclaurin polynomial for 1 over 1 minus x. So having said that, the reason I wanted to bring this up is that we can focus our attention inside here. I'll do it with, let me find a color here. I'm going to do it with green. We're going to focus our attention inside these parentheses and try to make it look just like that. So we're going to do basically substitution work. So based on that, if we do 1 over 1 minus, and it's negative x squared over 4 that we start plugging in, that means in our series here, we're going to get 1 plus negative x squared over 4, substituting it for x, plus negative x squared over 4, substituting it for x, but then squaring it, plus the same thing, negative x squared over 4 to the third power, and then of course we'll do the same thing at the end, negative x squared over 4 to the nth power. When I do that, that gives me now my power series for the internal portion, like it gives us the 1 over 1 minus stuff part. In fact, if I clean this up just to make sure it looks a little nicer, we get 1 minus x squared over 4, plus it looks like x to the 4th over 16, minus x to the 6th over 64. And then I'm afraid I'm going to run out of space here, so let me move this up just a little bit. And then finally our last little bit, plus dot dot dot. We'll have, for the last one, we'll have negative 1 to the n, x to the 2n, divided by 4 to the n. So there is the power series for the portion in green up here. Just the portion in green. I did a bad job circling it, just for that. Now, in order to finish this off, though, we have that part. What we want to finish this with is, of course, multiplying by the other spot. So in this case, I want to figure out what 5x over 4 times that thing is going to be. And of course, we just said it's in green. So that's the 1 over 1 minus a negative x squared over 4 that we're going to be multiplying it by. So when we multiply that through, that's the same thing as multiplying 5x over 4 times that thing, that expression we got for the power series, or the Maclaurin polynomial. So when I distribute that in, that's going to give me, let's see if I can do this correctly, it's going to give me 5x over 4 times this entire thing. Yeah, it's not the best, but we'll make this work. Hold on. Hold, please. There we go. So there it is. So that's what we're going to be distributing this 5x minus over 4, into. So when we do, that's going to give us our final bit. We'll have 5x over 4 for the first term, minus 5x cubed over 16 for the second term, plus 5x to the 5th over, it looks like 64 for for the third term, minus 5x to the 7th over 64 times 4 is 128 times 2, or 256. And then finally for that last term we'll have plus negative 1 to the n times 5x to the 2n plus 1. Because we had x to the 2n, we multiplied it times x to the 1. And then this whole thing is divided by 4 to the n plus 1. And that is going to be the power series that we were looking for. Voila, there it is. So what did we do? Basically, just to recap what it was that we did, we tried to transform our function, our rational function, which in this case was 5x over x squared plus 4, and we attempted to transform it into a form that resembled the one that represented the geometric power series, or corresponded with the geometric power series. Once we transformed it into that, by rewriting it as a bunch of stuff times something that fit that form of 1 over 1 minus stuff, or something, we're able to do substitution just like we always have before, at least in manipulating power series, and then multiply by all that stuff out in front, and we were able to get our power series just the same way. Now, having said that, because I modified this problem a couple different times here, I haven't checked the answer, so let's go make sure that our answer is correct. We do have the benefit of Wolf, it's already up, haha. We do have the benefit of Wolfram alpha, so let's write out the Maclaurin series for, and let's do it as 5x divided by x squared plus 4. Let's see what we get here. Okay, so it says our first three terms. Can we get more terms? Let's see if we can. Okay, it's always nice. So we've got our terms are, looks like, doesn't matter if that's hidden a little bit. We have 5x over 4 minus 5x cubed over 16 plus 5x to the 5th over 64 minus 5x to the 7th over 256. And then if we're looking for the series itself, yeah, there's series representation has imaginaries in there, and that's an interesting way to write it. But I feel really confident in what's there because we followed the pattern all the same. So there is the technique demonstrated. It's kind of a structural, like, make the two things mimic one another. It's kind of like you're sculpting algebraically, trying to make it look and resemble like some other piece of art that you saw somewhere. Trying to create some sort of approximation that's different and unique to you, but it's definitely accomplishing the goal of what was there before. So this is the technique. I had considered including a second example, but the truth is I think the Try It will do a good job of this. I'll have you working in both directions. It'd be something that if you want to see more examples of this, just let me know, and I can definitely produce content like that. So as mentioned, here is that Try It we were talking about. Just as with some of the Try It's from earlier in this unit, these aren't really conducive to writing into a Google form. It's hard to write the first 4 terms when there's so many different ways to do that. But in this Try It, I've got the first problem, which asked you to transform one of those rational expressions the exact same way. It requests the first 4 terms in the general term. So you're basically doing the same work that we did on the previous page. And then the second problem asks you to go backwards. I give you that power series for a rational expression, for a rational function, and I ask you to go backwards, which I think is a good challenge. It's definitely not easy, but I think it's a good challenge to get you thinking about how these things correspond and looking at structure in kind of the back direction, in the other direction. So as with all previous ones, I'll do written solutions for these Try-Its myself, and I'll just post them in the drive. Hopefully at some point post them so that they're visible too, in case you're not actually in my class and you're watching this. But that's kind of a phase 2 operation for this point while I try to get everything done. So having said that, I'll give you a few moments to work on this Try It. Obviously, I recommend that you probably pause it in just a second. I'll take a short break, and then I'll come back, and I'll do the second half of the lecture in just a few moments. So go for it. Okay, hopefully that was enough time for you to work through that Try It. Obviously, if you're just playing this thing through, it's pretty funny. I go, okay, take your break, go for it, and then hope that was enough time. Let's go from there. But again, hopefully you paused at this time and got some good practice out of those 2 problems. Again, I really think number 2 in particular is rich. But for us, I want us to move forward and take a look at the second half of the lesson. Now, as I said at the very beginning, the truth is we're not going to be doing anything completely new here today. We're just kind of approaching things from different angles, trying to extend our skill sets just a little bit. As it says at the top, the biggest reason for what we're doing today is because there's only a few really nice power series that have rules that we necessarily are going to remember and be easy to work with. But we can always create more if we just do some arithmetic operations on them. If we just kind of do those old-fashioned plus, minus, multiply, divide. If we just do those things, we can actually open up all sorts of new avenues. So now I said addition and subtraction are possibilities? The truth is, yes, they are. That would be something that's fairly straightforward, and I'll let you work through that a little bit if memory serves on the problem set. What I want to focus on today are two skills that are very straightforward, and they make good sense when you work through them, but they're difficult to execute, and that is multiplication and division. So what I'm going to demonstrate for you here on this problem and the next one that we'll look at are the two techniques and good organizational strategies so that you can be successful working with them. These are very straightforward, the steps make sense, but they're hard to do, they're hard to execute. So I just want to make sure that I demonstrate them very carefully for you. So this could go pretty fast, save for the fact that of course I'm trying to work through things very carefully. So in this problem first, we're asked to write p sub 4, the fourth Maclaurin polynomial for g of x equal to e to the x times cosine of x. So we have a product of two functions over there. Now keep in mind, before we begin, if we wanted to, we could just start differentiating e to the x times cosine of x a bunch of times, getting really long extended product rule produced derivatives, and then plugging 0 in. Gosh. And then plugging 0 in, so that way we could find what those values for the coefficients would be. The truth is, though, it's probably not the fastest way. And more importantly, because we have e to the x and cosine of x both as series that we know well, we don't really have to do that. We could just multiply their series together very carefully, of course, and we could end up getting our result. So where I'm going to begin this attack, if you will, is I'm going to begin by rewriting g of x in two separate colors. I'm going to write this as e to the x times the cosine of x. And the reason for that is just simply because I want to first visualize these as power series or polynomials that are being multiplied together. In fact, I think I'm going to call them polynomials for this point just for simplicity. So in here we're going to have two things that we're going to need to multiply through. So the first one is we need e to the x. Well, we know e to the x is 1 plus x plus 1/2 x squared plus 1 over 3 factorial, also known as 1/6 x to the third, plus 1 over 4 factorial, which is 24, x to the fourth. And at this point, I'll just point out that I'm putting all these extra terms here and hopefully not going to need them. I just want to include them there just because I'm not sure if anything's going to zero out. So I want to include a couple extra terms so that we're prepared in that event. So we'll start with that one. Second, we have to multiply by cosine. Cosine is the one that has alternating signs and even powers. So that'd be x to the 0 or 1. Minus 1 over 2 factorial, x to the second, plus 1 over, let's see, the 4 factorial. So that's going to be 1 over 24, x to the fourth. And actually, in this case, I don't think I actually need to go any further. I think the truth is I'm probably okay right here. And I just realized, like what I said before was incorrect. Like the truth is we're looking for the fourth degree, so it actually doesn't matter if they're zeroing out. We just need to go out to the fourth degree because it's possible we'll have fourth degree parts that show up. So having said that, here's what I want to do next. Next, I want to line this up so they're ready to multiply. Some people would love to just kind of do stuff like this and just kind of be blah, 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 and just kind of doing a whole bunch of stuff. My experience, though, is that it's very difficult to organize that, even if you're really, really comfortable using that kind of FOIL strategy. So instead, what I'm going to do is I'm going to be super organized here. I'm going to rewrite this first polynomial with lots of space along the side, along a horizontal line. And again, this is just my thought. This is just my strategy. If you prefer a different strategy, I mean, be my guest. Like, be successful, do what's best for you. I just have found that this has been a very successful strategy for this particular type of problem, where we're multiplying power series. So there is e to the x. The next thing I want to do is I want to prepare to multiply it by cosine. So I'm going to line up the terms in the appropriate spot. That'll be 1. We'll have minus 1/2 x squared. Then we'll have plus 1/24 x to the fourth. And of course there's more that's out there, but I'm not as interested in those because my hope is that going all the way to the fourth degree will cover us completely. Oh, of course it did that. I just wanted to draw a line. Okay, so now what I'm about to do here is something I've done before. I'm not sure if it's been in your class though, or if you've done it in the past. What I want to do is I want to multiply these together. So I'm going to multiply them just like we would old-fashioned problems. Like if I was multiplying 123 by 45, we'd do that same basic thing. We'd have 5, carry 10, 11, divide to 5, oops, excuse me, 6. We'd do all that good stuff that we had normally, and we'd be able to get our answer. So the motivation here is exactly the same as what you see right there on this side. We're going to kind of do this. The only difference is we're not going to have to worry about carrying or anything. We're just going to have to worry about matching up terms that have the same degree. So let me demo this. I'll start this with a single line. I'll start first by multiplying the pink number 1 by the top row. So when I do that, that's going to give me the literal top row. 1 times 1 is 1, 1 times x is x, 1 times 1/2 x squared is 1/2 x squared, 1 times 1/6 x to the third is exactly that. You get the picture. And notice as I do this, I'm leaving the terms underneath their appropriate degree. That way all the 4th degree terms are here, all the 3rd degree ones are here. That's just another recommendation that really keeps things organized for you. Just seems to really help in the long run. Okay, we've done that. The next thing I'm going to do is I'm going to now multiply this term, the minus 1/2 x squared term, by the top row as well. So when I do, that's going to give me first 1 times negative 1/2 x squared. That's going to be negative 1/2 x squared. Means we only have to start right over here. So I'm going to start right there. Then we'll have minus 1/2 x to the third. Then we'll have minus 1/4 x to the fourth. And of course there'd be more stuff here, but we don't have to worry about them because we're only interested in, as it says, the 4th degree polynomial. So we've done the second term. Let's go do one more. Let's see, pick a good color here. Let's pick the plum color. So I'm going to use the plum one to deal with the 1/24 x to the fourth. So I'm looking at this last term that we see on that second line in pink. Now when I multiply 1/24 x to the fourth times 1, that gives me, of course, positive 1/24 x to the fourth. And from there, there'd be more terms. But keep in mind, all we want to do is get the 4th degree polynomial. So the truth is, we don't need to multiply anything else out. If we multiply 1/24 x to the fourth by x, we'll get something of degree 5. That's bigger than what we're interested in. And if we went any further out in the cosine function, we'd be looking at x to the 6th, which wouldn't produce anything to the 4th power either. That means that we actually have everything that we need here. We've done our work. We've done our stuff. Which means that now all we have to do is add all these things together. We'll just do the arithmetic. When we do, we'll just bring down the like terms. That'll be 1 plus x. Notice the x squared, 0 out. We have 1/2 x squared minus 1/2 x squared. That zeroes away, so we're good. On the next one, we do have to be a little bit careful here. We have to do a little bit of work. We have 1/6 minus 1/2. It's the same thing as 1/6 minus 3/6, which is going to be negative 2/6. Or negative 1/3 x to the third. And then finally for the last one, if we do the same kind of thing, we have 1/24, 2/24, but we're subtracting a fourth. Let's multiply up and down by 6, and we'll get 6/24 x to the fourth. That's 2/24 minus 6/24, which is negative 4/24, which is the same thing as negative 1/6 x to the fourth. So what that tells us is, after doing that work, we can draw our conclusion up here and state that e to the x times cosine of x is going to be approximately equal to, and it looks like 1 plus x minus 1/3 x cubed minus 1/6 x to the fourth. And there is our 4th degree polynomial. So although we said that that's e to the x cosine of x approximately equal to it, we could then instead say that this is p sub 4 of x, as requested. So there it is. There's our work. All we basically did here was multiplication the old-fashioned way. The only thing to note, though, is, of course, this organization strategy is just really helpful. I think it maximizes your likelihood of being able to execute a problem of this level. This is a pretty straightforward example. Things cleaned up pretty nicely, and the denominators didn't get too prohibitive. But at the same time, the strategy itself is really effective. So if you're multiplying two polynomials together, two Maclaurin polynomials, Taylor polynomials, power series together, I highly recommend this thing. I usually call it the 3rd grade method version. It's not a technical name, it's just this resembles the 3rd grade multiplication I was taught in Miss Filioni's class back in 1995, I want to say. So having said that, maybe this will be a useful technique for you. Otherwise, make your rainbows to the heart's content. It's tough to execute a large multiplication or product like this with. So there is our first thing to demonstrate, the arithmetic operation of multiplication between power series. The Second thing we want to demonstrate is kind of along the same vein, and once again we want to find some particular terms for a particular Maclaurin polynomial. In this case we want to do it for the function tangent of x. Now as I bring this up though, of course, you might think to yourself, it's easy enough just to differentiate tangent of x, and yeah, you're not wrong. Like the derivative of tangent is secant squared. The problem is once you get past secant squared, then you start having to take the derivative of things like secant squared, which I believe is 2 secant times secant tangent, which would be 2 secant squared times tangent, and then suddenly the product rule and chain rule part just becomes a little bit nastier than maybe you'd like to. So it's only necessarily valuable, it's only a valid approach for a couple steps to like differentiate your way through it. So what we want is a way to handle something like tangent of x. So just like before, it's important to figure out structure here. The difference is, although we were told on the last problem, e to the x times cosine of x, tangent of x we have to anticipate a little bit. And unsurprisingly, if we did multiplication first, we want to demo this one as a tool for division. So we want to try a quotient here and see if we can get our way through. And I'm going to attempt exactly that. I'm going to rewrite tangent, of course, with the quotient identity of sine of x over cosine of x. And I'm going to divide those two out and see what happens. So starting here, this is an important place to begin because it lets us set up the actual quotient for us. So if we're trying to process what this is going to look like, tangent of x equals sine over cosine, it's important to establish what those terms are for the polynomials that we're going to be working with. So in this case, sine is the one that well actually we just used cosine, so I might as well write that in. 1 minus 1/2 x squared plus 1/24 x to the 4th. I'll even put one more term, 1 over 6 factorial, which is 720 x to the 6th, plus dot dot dot. So that way we've got a few terms to work with there. So hopefully good shape. In our numerator, we have sine. Sine's the opposite of cosine. It's still going to be alternating, but it's going to have all of the odd terms, odd degree terms. So that'll be x minus 1 over 3 factorial, or 1/6 x to the 3rd, plus 1 over 5 factorial, which is 1/120th x to the 5th. And then for this next one, I happen to know it's 1 over 50/40 x to the 7th, plus dot dot dot. So there's what we're going to be dividing here. I was going to say differentiating, but no, we're trying to avoid that differentiation. We want to work through this mess. And now in this question, I'll also point out that because it asks us for the first 4 non-zero terms, it's not as simple as going out to the 4th degree like we did before. I'm not sure how many powers or how many lines of division we're going to need to go through to get 4 non-zero terms. So having said that, I'm not even meaning 4 non-zero terms. I actually meant 3 anyway. I was just looking at my work from earlier, and I do not want to work through 4 non-zero terms of this, and you don't either. So we're going to go 3 non-zero terms. You can't do this yourself, but I can help out when I can. So instead, we're just going to include a bunch of terms. We're not sure which ones we're going to need, so I'll just keep as many as possible here, just in case. So having said that, now my job is going to be to prepare us to actually perform the division. So in here, let's see if this will help me. Yes. I want to write this in again, like a 3rd grade style of division. I want it to resemble what I always used to do when I performed long division back in the day. So, and again, you may have done it in a different year. I'm not sure how math has worked for all of you, like when everything pops up nowadays. But I imagine it's in that 3rd, 4th grade kind of range when you're working through long division and stuff, your first full inverse operation. For here, I'm going to set this up. See if I can get that thing just look a little bit nicer. Okay, well, that's as nice as it's going to get. So here we go. Okay, so now that we have the division set up, our job's going to be to actually start to figure out how many times do certain things go into certain things. So when you first start this off, this might feel like it's language you haven't used in a long time, but that's okay. But it's good to have it in there. First question I'm going to ask is, what do you multiply 1 by to get x? The answer to that is, of course, you multiply by x. So there's my first move. When I do that, once I have x, I then have to distribute that x into all of the terms of the other polynomial, which would be an infinite number, but of course we'll get there eventually. So if a term's positive, I'm going to leave it as positive, or I'm going to not write the sign in, so x times 1 is x. The next one will be minus 1/2 x to the 3rd. Next one will be 1/24 x to the 5th. The next one will be minus 1/720th of x to the 7th. And of course there'd be more, but we're just not going to go too far. We'll just kind of go from there. Now, having said that, the next move, something that I've been using since Miss Nakamura said that to me a long time ago when I first got to Franklin, is next we're going to draw the line and change the sign. So now that we have it in there, I'm going to draw the line I just did and then change each and every sign. So having done that, what we can now do is subtract away and see what's left over. So in this case, we have x minus x is obviously 0. That was our goal anyway, to eliminate that part. Now we have minus 1/6 plus 1/2. It's the same thing as 1/6 plus 3/6, which will give us positive 2/6 or 1/3 x to the third. On the next one, this can be a little bit tougher, but remember 1 over 120 is 1 over 5 factorial, and this is 4 factorial. So we can rewrite that as 5 over 120. That's going to give you minus 4 over 120, or minus 1/30 of x to the fifth. And then this next one, kind of following the same pattern, this is 6 factorial and 7 factorial. The truth is, I'm not sure what's going to happen there. I could finish this up. Since that's 7 factorial, we could then do this as 7 over 50/40. And the truth is, then we could get something like plus 6 over 5,040 x to the 7th. But the truth is, I'm really hoping that we're not going to need that. So I'm going to put it on there. I'm not going to simplify it, but I'm going to cross my fingers that I'm not going to need it. I'm pretty sure I won't, because I can look at my work from earlier preparing for this, but still, we'll play along. Okay, now that we've done that, we get to move to our second step. And I'll change the color as we go here. I'll go to pink. So next we need to look at this. The question becomes, what do you multiply 1 by to get 1/3 x cubed? And the answer is, of course, you multiply by 1/3 x cubed. Having that 1 there is really helpful. So once that's in, of course, just like before, we're going to distribute that expression into all of the parts that we have. So that's going to give us a 1/3 x cubed. For the next one, it'll be minus 1/6 x to the fifth. Then it'll be plus 1/72, because 3 times 24 is 72, times x to the 7th. And yes, I definitely don't want to have to deal with that, but we'll see what happens. At this point, I'm going to draw the line and change, oops, I didn't change the color, speaking of changing. Draw the line and change each sign. So there's our stuff. Now when we combine them, of course, the first one goes away. This then leaves us minus 1/30, and then we'll change 1/6 to 5/30. That's going to give us positive 4/30. So I'll write that down just for simplicity. And then the next one, I'm just going to put, I don't really want to do that term, so I'm going to be pretty confident that we're going to be okay. And the reason I say that is then our final step here would be to compute this last one. So just like we did in the last one, we'll ask ourselves, what do you multiply 1 by to get 4/30 x to the fifth? And if we do that simplifying right now, we'll get plus 2/15 x to the fifth. Once we do that, we'll end up right down here, 2/15 x to the fifth. We'll also have other things. I guess it would be technically a minus. It'd be minus 1/15 x to the 7th. But I'm not going to worry about that, because the important thing is, when we draw the line and change each sign, we get a 0 in that first bit. So we do have other stuff that we could look at. But remember, thanks to that opportune change that I made, we only wanted 3 terms. And oh geez, I asked for the general term here. Oh, I'm so full of errors here. The general term is awful to try to find. That's what I get for trying to copy nicely written instructions. Yeah, we're not going to find the general term for this guy. I believe the general term involves like Bernoulli numbers, if memory serves. You can look that up if you're interested. Like, oh no, we're not going to do that. Every year I tell myself, oh, I'm going to find the general term, and then I go, no, I'm not. It's a lot. So instead, let me just point out that what we've just accomplished is what we were looking for in the first place. We wanted the first 3 non-zero terms of tangent of x. That means we can now say that tangent of x is approximately x plus 1/3 x cubed plus 2/15 x to the fifth. And that is the result we were looking for. We've got 3 non-zero terms. Granted, we could have extended to the 4th, but it's just going to be so messy. I don't think you want to do that, and I definitely don't want to do that, not going to lie. So it's not necessary. Like, the idea of division is here. You got to see the technique demonstrated nicely, and obviously the higher the degree terms, the more tough it is to combine those coefficients. but this is all we're asking for. I'd be very reasonable if I was asking you this on an assessment, as would I suspect College Board. Although again, in 2020, I believe this has already been removed from the AP exam curriculum, so just for what that's worth. So having said that, what we've now seen is you've gotten to see an example of my organizational strategy to multiply two power series together to generate a power series for a product that might be prohibitive using differentiation. In addition, we got to see the quotient process of two power series or two Maclaurin polynomials to again give us a, what's the word I want here? To give us a Taylor polynomial that would otherwise be really difficult for us to come up with, or Maclaurin in this case. So having said that, that completes everything in the second section of this lecture. So I'd love to give you an opportunity to test out this technique for yourself, and I really highly recommend, I can't endorse it enough, but I'd love to see you using that written out technique, kind of the third grade style of multiplication and division, just to organize your work. I feel very strongly that it's probably the best organizational strategy that you have out there. Of course, if you have more, a better strategy, I'd love to hear about it so that maybe I could consider integrating it in myself in the future. For now, though, here are two try-it problems. I wouldn't call them quick because you're multiplying and dividing power series, but two solid problems for you to work with to demonstrate and practice with these techniques. And so I'm going to give you a little bit of time here in just a second to work through those, and of course the answers will be available in the usual places. When we finish, we'll just have one last little thing for us to throw together just as kind of a quick little demonstration about just how kind of neat these processes are, and then we'll call it a day. So having said that, please do take a look at these, and then we'll be right back. Alrighty, hope you're good with that amount of time. Hopefully that was enough for you to work through these power series operations of multiplication and division and to get comfortable a little bit with the kind of onerous task of actually working through and executing the multiplication and division of very long and extensive, technically infinite power series. Having said that, the last thing I wanted to wrap up with is not something new. It's not new curriculum. It's just kind of one of those cool moments where you can realize just how neat this approach gives you. It opens up lots of possibilities for things that we just necessarily wouldn't have even thought of, and reaffirms some identities and knowledge that we've had before. What I mean is this, here's where I'm going to start. So I'm assuming that as I move to this next page that you did do these try-its, particularly number 1, which focuses on the first 3 non-zero terms of sine squared. So from there, let's just point out something that's kind of cool. And I like to be able to call out some of these facts as much as possible, just because it just kind of blows my mind, for lack of a better word. It's one of those few moments where I really stand in awe of mathematics in general. So if you'll recall back to pre-calculus, I wrote it on here twice, and see that I'm actually rewriting everything so it looks as nice and as clean as possible. In my mind, every single time I'm thinking I need to make these words bigger for Brittany, but, hi Brittany. But also, obviously, everyone else as well. So what I want to point out here is as you look at this, that identity back there, the Pythagorean identity, sine squared plus cosine squared is equal to 1, you might think to yourself, that's a whole different branch of mathematics, like hardcore trigonometry. That's not what we're focused on here. But the truth is, this identity, if it holds for any sort of triangle, it should hold using Taylor and Maclaurin series as well. So keep in mind the work that you just did in that try-it. You found the first 3 non-zero terms of sine squared to be x squared minus 1/3 x to the 4th plus 2/45 x to the 6th. Likewise, if you desired, I'm not going to demonstrate this because I don't think you need to see it, but if you wanted to, you could work your way through and you could figure out what the power series is for cosine squared. So this gives us cosine squared right down here. Actually, it's a very ugly line. So close enough. So there is cosine squared. So again, assuming that you trust my calculation, but I haven't really led you astray too often, other than that whole McGillicuddy thing, which somebody's probably still remembering. Let me point out that it turns out cosine squared is equal to 1 minus x squared plus 1/3 x to the 4th minus 2/45 x to the 6th, and then more stuff. But I want you to notice something kind of neat here. If we combine these two things together into sine squared x plus cosine squared x, look at what we get. I'm going to have to do it on 2 lines so we can see it here. Sine squared, yeah, of course it wants to copy the whole thing. Couldn't possibly give me a little bit of room here. So if we look at sine squared, first and foremost, sine squared is equal to this. And actually, you know what? I'm going to give myself a little more space. I apologize. I thought I had more room than that. I did not. So let's do this. Cut that out. There's all that calculation I just saved us both from. So there's where we are. We've got sine squared. Okay, so there's what we got. There's sine squared being put in. Next, we want to talk about cosine squared. And we can steal cosine squared from right up here. You can see this Windows journal is not being my friend right now. But that's okay. So what do we got? Oh, and of course it's going to be blocked by my head. Ah, jeez. This is so frustrating to just not quite have enough room. There we go. That should be okay. There we go. So there it is. All that work just to set up addition. What I want to point out, though, if you can't see it already, is look very closely at those terms, which again we found without necessarily showing all the work. But notice that we have x squared minus x squared, minus 1/3 x to the 4th, plus 1/3 x to the 4th, plus 246x to the 6th, minus 246x to the 6th. After all of that, can you see the only thing that's left over? That guy. This whole expression on the right is just equal to 1, which of course it is. We know that's the identity sine squared plus cosine squared. But the interesting thing was that even if you take this massive mathematical and algebraic detour into the Maclaurin polynomials for sine squared and cosine squared respectively, you still end up getting literally equal to 1. Because that's what makes this structure true, is it's true across all sorts of domains and interesting places. And the truth is, although we're just talking about a trigonometric identity, there's so many more powerful things that are out there. I don't think we'll get to do it, particularly in the pandemic version of Calculus BC that we're looking at right now in 2020. We won't get to do that final thing, but actually, if anyone's ever seen my license plate, there's an identity, a mathematical or arithmetic identity in there involving complex numbers that can actually be shown using power series as well as some of the cosine plus I sine stuff that's out there in that same ballpark. So there's really neat things that are out there. For now, I just wanted to kind of show that to you because it still fascinates me. Even now, as I'm standing at home talking to a digital camera, I still find that kind of like cool feeling of like, oh, it's so neat that that works out. But of course, I saved you the trouble of watching me compute a massive product. So you're welcome. What can I say except you're welcome? But that's about it. So just as kind of a quick little recap of what we did today. We began by opening up by talking about the special power series and then augmenting that list with one more, which turns out to be what we call the geometric power series. It's called the geometric power series because it's literally a geometric series, which means it bakes in the interval of convergence for us, so we know exactly what that is. Afterwards, we looked at the algebraic manipulation necessary to allow us to find the power series for any rational expression or rational function, at least one that fits the form of the geometric power series, and we just did a bunch of kind of finagling and little techniques to slowly massage it into the function we were looking for and then producing its power series. Gave you a chance to try that yourself, going in both directions. After that, I demonstrated what I call the third grade method for doing extended multiplication and long division of power series, just the same way you would have with numbers. I just made it really organized and really colorful, and truthfully, when I look at this, it's really sharp. I'm not gonna lie, I think this looks really nice. I'm proud of my efforts, so be proud of your efforts too. And then finally, after letting you practice that technique a little bit, I just kind of showed you something that wows me that probably doesn't wow you as much, but hey, I'm in the control of this and no one's here to stop me. Nobody laughs at my jokes either. I press this button. You've been eliminated. Not really. So the button didn't work for a second. So anyway, thank you for watching this video. Hopefully it was a nice reprieve from kind of the conceptual and algebraic work we've been doing the last few days with manipulating in both interval and radius of convergence. Nice to just kind of do some operations and just kind of grind through the pure mathematics or the pure arithmetic of this kind of situation. So as always, I hope you're staying safe and staying well. I wish that I was delivering these lessons to you in person, but that's not looking like what's in the cards right now. But obviously I miss you, and I wish you and your families the best as you face all of this stuff whenever you're watching this video. So have a great rest of your day. It's always great to pretend to see you, and good night.